Now, like I said, the question is how to efficiently represent these Boolean feature constraints. In realistic product lines, I told you can have hundreds, if not thousands, of features, and therefore also, of course, these constraints. They can get very large, right? And the question is how do you deal with this? So we must find a finite representation of conjunctions and disjunctions, right? And it must be finite in order for all of this to terminate, of course. But it should ideally not just be finite, but also small, right? So we want to be able to also reduce Boolean expressions efficiently. And ideally, we would actually like to have a normal form. Why is that important? Well, if we have a normal form, it basically means that any two equivalent Boolean constraints, they will normalize to the very same normal form, right? And that means that we can then easily identify when a fixed point has been reached, because then we will easily see that, if, for instance, we go through a loop twice, and then the second time we actually have the same constraint, nothing changed anymore, then we have reached our fixed point, right? If you don't have a normal form, that might be more of a challenge. And yeah, so what do these normalizations look like, right? So you can have easy cases if you have something like f and g and then f, right? This should reduce to f and g only, for instance, right? So those are the kinds of normal forms that I'm talking about. But there are a number of different normal forms that are out there, right? And some of you, I hope, have already learned this in the first years of your computer science degree. So you can use conjunctive or disjunctive normal form, for instance, right? So in conjunctive normal form, you have a big conjunction of individual disjunctions, like you see here. And this is the only allowed form. And in disjunctive normal form, you have the opposite, right? So you have a large disjunction of individual conjunctions. But what's already showing here, so these are actually the same constraints, right? And so if you have a constraint that is relatively small in CNF, but then for some reason you need to convert it to DNF, that can give you a very large blow up. And the other way around, it's actually the same. But if you want to do, for instance, a conjunction here, that is relatively easy. You just add another conjunct, right? But if you want to do a disjunction, that's actually hard because you need to touch all of these different disjunctions here. And the other way around for DNF, right? So for CNF, there are certain operations that are efficient, others not. The same for DNF, right? So that's exactly the problem. And that's why we are interested in other representations as well. So in SPLift in particular, we decided to use so-called ordered binary decision diagrams, or OBDDs for short. And they represent another possible normal form. The nice thing about BDDs in general is that they can encode both CNF and DNF at the same time in one efficient representation. And they have a normal form, and so the test for true or false or even equality can therefore even be implemented as a constant time operation. So basically it means you reduce, when you construct an OBDD, every time you reduce it immediately to its normal form. And that also means that you will never have any two different yet equivalent OBDDs at the same time. That simply cannot happen. You will always cache this normal form then also. And that's why these operations are really quick, right? So basically, if you're looking at two OBDDs, either it's the same and then it will be equal, but if it's not the same, you're guaranteed that it's not equal. And this is what an OBDD looks like for this particular Boolean constraint here. So an OBDD always contains these two nodes at the bottom. So this represents true, and this represents false. And now we have these differently labeled edges for the true and false case. And now this is basically telling us this constraint here, it should be true when A is true, right? So then we should immediately go to true, right? Because then that makes the entire constraint true. Or else, if both B and C are true, right? So that means you have to have a true B edge, but then also a true C edge. And only, along this path, then do you also reach true. And in all the other cases, you go to false. And now the nice thing is that this basically has a DNF and a CNF embedded. How can you observe the DNF here? Basically, if you do the following, so for each path P to 1, you conjoin all the edges on P, and then you disjoin the result. So here we have two paths, the red ones, that bring us to this one node, to the true node. And we take both paths and do a conjunction along each path and then a disjunction in the end. And that then gives us the DNF. And that's actually, in this case, it's what you see here, right? So that's actually already a DNF representation. In this case, it's a bit more explicit, okay? For instance, you could do this particular, if you really thoroughly follow this algorithm, then you're also picking up this not A here, right? So basically you have a not A here and B and not C. But then again, if you were to simplify this, it's basically the same constraint that you have up here. Now, let's take a look at CNF. So the same formula in CNF, it looks like this. And now you basically compute this doing exactly the opposite. So for each path now to 0, you disjoin the negations of all the edges on this path, and then you conjoin the result. And again, if you do this now for the red paths that you see here, then this gives you the following. And again, that's basically the same as you have up here, right? It's a bit more explicit, but it's basically the same constraint. And now the thing is, because both of these are embedded, these OBDDs, they basically have efficient conjunction and disjunction operations. So you can actually do them not necessarily in constant, but in polynomial time. And that makes it actually a relatively runtime efficient representation. One challenge, and that I will talk about later, is that it's not necessarily a very memory efficient representation. So these OBDDs, they can grow large, and even worse, their size actually depends on the ordering that you choose here. So here I've ordered it in the way that we start with A and then with B and then C and so on, but I could have chosen a different ordering, and depending on the constraints that you have, different orderings might be optimal. They are all valid orderings, they all give you valid OBDDs, but they give you different sizes. And finding an optimal ordering for an OBDD, unfortunately, is NP-complete again. So it's not efficient. Therefore, you have to apply certain heuristics to find a good OBDD ordering. Now, once you have any representation of your feature constraints, there's an additional trick that you can play. And that is taking advantage of a feature model. This is actually a feature model for one of the example product lines that we used for the experiments that we ran using SPL-Lift. But you can see it's already sizable, but in terms of real world product lines, it's actually a small feature model. But the point is that out of this feature model, you can generate a Boolean constraint. Obviously here it will already be a sizable Boolean constraint. Now for the sake of an example, let's assume it's simply this constraint here, right? So this is giving us a feature constraint f exactly if g, right? And now let us assume that the static analysis, so SPL-Lift, it has computed this feature constraint here, right? That's exactly the constraint we saw earlier. So the static analysis is telling us that we may have a data leak, but only in a situation where G is true and the other features are false. But now the feature constraint that comes out of the feature model is telling us basically that this is not at all a valid configuration, because the feature model is telling us that only those configurations are considered valid where F and G are enabled at the same time. And that's not the case here, right? So basically this means the static analysis, it detected a false positive, right? So it detected a data leak, but only in a configuration that we will never actually compile because it's not part of the feature model. And we can figure this out automatically by simply taking the feature constraint that the analysis computes and doing a conjunction with the feature constraint that comes out of the feature model. And if this is false, like it's the case here, then we know that this is actually an unrealizable situation. And now the naive way would be to do this conjunction in the very end, right? So we take the results that the analysis has computed and we do the conjunction with the feature model then. But there's a better way to do this. Namely, we can do this on the fly, right? So already when we compute the jump function to this program point and basically do the conjunction with this constraint here, we can not just do a conjunction with not f, but we can also do a conjunction with the feature model constraint. That will take a bit more time at this program point because this model constraint, it needs to be considered. But the advantage is that likely this constraint that we are computing here, it will already be reduced. And in the best case, it might even be reduced to false. And if this gets reduced to false, then in our abstract domain that we're using for the IFDS solver, false is actually the bottom element. And that then automatically causes the IDE solver to terminate the computation here. So it's basically saying this value is now definitely untainted. And then it's no longer tracked, right? So this means already at this program point, in this case, then the analysis could already discontinue, right? And at the latest, for this particular program, this will actually happen here, right? Because here we get this feature constraint, not f and g. And now if we have a feature model constraint that tells us f if and only if g, then this is mutually exclusive to this constraint here, right? So this will reduce to false. So that means if we do this for this program, then at this program point, actually the analysis will already terminate. Now, this is BDDs, and like I told you, they have some advantages, but unfortunately, they also have some disadvantages, right? So BDDs, they tend to get rather large, and therefore analysis of real-world, large-scale product lines, therefore, they seem to require some other representations. And this is actually subject to current research. So we're currently working on this. I will still be telling you a few words about a current prototype that we are building for C and C++. And there we are already following a slightly different model. That's all I wanted to say about BDDs for now. I will still telling you a bit more about how this approach then actually works in practice, what results we obtained, and also this current research prototype I talked about.